Okay, so we've been presented with an unidentified compound, and we've been told that it contains aluminium and oxygen, right? And we've been asked, well, work out the empirical formula. In the question, we've been told that it's got a particular composition in terms of the percentages by mass of the two elements. And what I'm gonna do is I'm gonna just do a check and see, well, what's the total out of those percentages. And so I would invite you to have a go to see what you get when you add those up. So in this case, if I add them, I'm gonna do 52.94 plus 47.06. I mean, by visual inspection, you might be able to just know what it adds up to. But if you do calculate that, you should find that you're gonna get 100. Now, this is valuable information. It gives us an idea of what we're. If we do make any subsequent assumptions, it gives us an idea of what the original number was. In any case, at this stage, considering what we need to figure out, the empirical formula. We're looking at, well, what is going to be the simplest whole number ratio, right? And in order to get to that point, we're going to need to compare the amount of substance, which is not easy to do when it's in this particular form. However, if we can convert it to an amount of substance type of comparison, that would be much easier. So that's what we're going to do. So the assumption we're going to make in order to get it in that direction is we need to establish a mass, right? So because obviously to get it to amount of substance, n moles is equal to mass divided by molar mass, right? In grams per mole. So what we're going to need to do is we're going to need to convert these to masses. So we'll assume that this is actually this sample, this specific sample we're dealing with for the purposes of this question has a total sample size of 100 grams. And so therefore what we can do based on that assumption is we can say for the aluminum, right, it's actually 52.94 grams. And for the oxygen, we can say that that's 47.06 grams, right? Now, we want to convert this, as we said, to amount of substance. And we can see from this equation that what we need to do with the masses to convert it to an amount of substance is we need to divide each of these by their respective molar masses. And we can get that from the periodic table. And you may already know what the molar mass for corresponding with oxygen is, right? Which is 16. But nonetheless, we're going to go through the whole process. We're going to go to the periodic table and work this out. Okay, so we've got Al, and I'm just going to put this here. So for Al, we can see the relative atomic mass is 27, right? It's 27. And so that's effectively the molar mass. And for oxygen it's 16, right? So for oxygen we can see it's 16. So we're going to just write these out so that we can do the calculations. So MR of Al is going to be equal to 16. No, not 16. No. It's going to be 27. And the MR of oxygen is going to be 16. Yeah. Okay. Now, oh yeah, by the way, this is, as we said, as I showed in the equation before, these molar masses are in grams per mole, right? So they're grams per mole. Okay, right. Okay, so the other thing we're going to do here, okay, we're going to do divide that by 27, and here divide this by 16, right? And I invite you to have a go and work those out. See what you get when you do those calculations. So now we're going to say N equals effective, and then just write down what the ratio is, right? So I'm going to give my answers in this case, like for this particular step, to 5 decimal places. Okay, so it's going to be 1.96074 for Al. For oxygen, it's going to be 2.94125. Right, and as you can see, we don't have a whole number ratio at the moment. We have something that's quite close to a whole number ratio, right? I mean, if we did happen to round the Al value to 2 decimal places, we wouldn't get a whole number. But if we rounded it to 1 decimal place, I mean, we would, but I'm not going to do that because in this instance, rounding this is not going to really get us there. So we'll do the extra step and see if we can get closer before doing any kind of rounding. So the smallest value, if I want to force an integer, what I'm gonna do is I'm gonna divide both values here by the smallest one, which is in this case the molar value associated with aluminum in our setup. So I'm gonna do that. So divide that by 1.96074, which is of course going to give us 1 because we're dividing it by itself. 1.96074. So I'd invite you to work out what that is on your calculator. See what value you come up with for that, and that's going to be 1.50007. Okay, so based on this, what we're actually going to be able to do from this point going forwards is, well, you can see quite clearly that this 1.5 is very, like, it's well, we're going to do a scale up, but you can kind of see where this question is headed. We can see what, roughly. So at this stage we need to get that to a whole number, right? But how are we going to do that? So we're going to do it by a scale up process. Multiply it by 2, multiply it by 3, multiply it by 4, up to the point necessary anyway to get a very close to a whole number on both sides. But in this particular case, it's 1.5, and I think we would know that effectively 1.5 when we multiply it by 2 is going to give us effectively what it's very close to a whole number. But we're going to let's go through the calculation, right? So to multiply it by 2, and of course, if this wasn't the case, if we were dealing with something like I don't know, a 1.75 or a 1.25, something like that, we might not, like, it may not simply be a simple case of, okay, multiply it by 2 and sort this out, right? So but in this case, this is what we're dealing with, a 1.5, right? Okay, so multiplying both sides by 2, we're going to get a 2 here, and here we're going to get a 3.00014. Okay, and now looking at this side corresponding with the oxygen, you can see that if we round it to 2 decimal places, in fact in this case it's even if you round it to 3 decimal places, you get a whole number. But in any case, 2 decimal places, you get a whole number. So let's round this, and this is already a whole number, so we round the one corresponding with oxygen. You're going to get 2, and it's going to be 2 to 3. Okay, and remember, so this is aluminum, this is oxygen, right? Therefore, what you're going to be able to say, so we can say that Al is going to be Al2, and for oxygen we can say O, and we can say 3 would correspond with that, right? And effectively that gives us what? It gives us Al2O3, right? Al2O3. And in this particular case, I mean, if you divide Al by 2, you will not get a whole number corresponding with the oxygen. If you divide the oxygen by 3, you don't get a whole number corresponding with the aluminum. So we can say comfortably that, yes, this is our simplest whole number ratio, right? And so therefore this is, in this case, the empirical formula. Now, this particular compound, although this is an empirical formula, if you look at it from a molecular perspective or molecular formula perspective, actually this is a very important compound, right? So this is aluminum oxide, right? The other name that is given is alumina, right? And this is actually very much it's quite key in the production of aluminium, right? Globally, the production of it is in the on the scale of hundreds, well, over 100 million metric tons per year in global production in recent times of this, and most of that production of that aluminum oxide is used to produce aluminium, right? So as a metal, you know, so yeah, you know, feel free to look into that yourself. Like, you can look into the structure and whatnot. Okay,